Now that we've talked about alkenes, let's start talking about the reactions that generate alkenes. These are called elimination reactions. In this video, we'll talk about different mechanisms that could lead to elimination. They can be, just like substitution, they can be either concerted or stepwise mechanisms. And then we'll focus for the rest of the video on the E2 reaction, its mechanism, the types of substrates that undergo E2 reactions, and the orbitals that are involved in those reactions. So in the previous video, we mentioned the possibility that a compound with a leaving group can actually undergo two types of reactions. In the past, we've talked about substitution reactions. So hydroxide is a good nucleophile. It could substitute for the bromide to give the product of substitution. However, in this video, we'll talk about instead of acting as a nucleophile, hydroxide can act as a base, and when it does so, it will give a product of elimination, which is an alkene. The reason why these are called elimination reactions is because you could imagine that if you go from starting material to product, it looks as if we've eliminated a molecule of, if this leaving group was bromide, for example, HBr was eliminated to give an alkene. So that's why these are called elimination reactions. Let's remember that when we're drawing the mechanism of the E2 elimination or any elimination reaction, we have to use one of the four allowed moves in organic chemistry. We can only do a nucleophilic attack step, a loss of a leaving group, a proton transfer, or a rearrangement. There's only four kinds of arrows, and those are the types of arrows that we're going to use to describe elimination reaction mechanisms. Okay, so let's talk about two possibilities for elimination. Remember, when we talked about substitution reactions, we said you could either have concerted mechanism or a stepwise mechanism. That's going to be exactly the same case here. So if we have a concerted mechanism, what's happening is a base is doing a proton transfer. It's abstracting a proton at the same time that we're forming a pi bond, at the same time that the leaving group is leaving. So we have three arrows, they're all happening in a single step to give a single alkene product plus the leaving group plus the protonated base, which isn't shown here. So remember, for a concerted mechanism, the proton transfer happens at the same time that the leaving group leaves. But in the concerted, in the stepwise mechanism, just like in the SN1 reaction, right, the leaving group leaves to generate a carbocation, but instead of nucleophilic attack, a proton transfer occurs to give the alkene. In this video, we're going to focus on this concerted mechanism. In the next video, we'll focus on the stepwise mechanism. So again, remember when you're drawing your arrow for this, you want to show the arrow coming from the lone pair of electrons and forming a new bond to the hydrogen. These two electrons are becoming a carbon-carbon double bond, or these two electrons are becoming the pi bond at the same time that the leaving group is leaving. One way to think about this, right, is that this is like an SN2 reaction, except instead of a nucleophile attacking this carbon, the nucleophile are these two electrons, which are then pushing out the leaving group. Okay, so let's say that we had this question and we were asked to draw the mechanism. What we're going to draw here is we're going to start off by drawing the bond to the hydrogen, right? So this carbon is only bonded to one hydrogen. It was bonded to two hydrogens, so one hydrogen got removed. Sodium methoxide in this reaction will be a strong base, which will be removing that hydrogen. So we're going to draw an arrow from a lone pair of electrons to the hydrogen. So that's forming the OH bond in methanol. These two electrons are becoming a pi bond, and these two electrons are becoming a lone pair on bromide. So this would be the concerted mechanism of this particular reaction. This is an E2 reaction, right? Which means that the kinetics would depend on the concentration of the base and the substrate. So the rate of this reaction is equal to some rate constant times the concentration of the substrate, which in this case is this bromide, times the concentration of sodium methoxide. It's bimolecular kinetics. Remember, think about this as, at least in terms of kinetics, similarly to the SN2 reaction. Notice that everything is happening in one step. So if we decrease the methoxide concentration, that's going to slow down the rate. If we decrease the electrophile or the substrate concentration, that's going to decrease the rate. So the rate depends on the concentration of both of these. Right. So we have a single step. The base is picking up a proton. We're forming a pi bond. The leaving group is leaving. So the rate is going to depend on the concentration of both the substrate and the base because we only have one reaction. Let's say that we were asked to draw potential energy diagram. Remember, it would be one step. It'd be an exothermic reaction, right? Because the products are more stable than the reactants because the reaction went. And if we were going to draw a transition state for this particular reaction, we'd want to show that this bond is partially broken. This bond is partially broken. This pi bond is partially formed, right? And this bond between the hydrogen and the base is also partially formed. So we have this bond partially formed, this bond partially broken, this bond partially formed, this bond partially broken. Remember, when you're drawing the transition state, right, each arrow can give you a clue, right? This bond is forming, so it's partially formed in the transition state. This bond is partially broken, so it's partially broken in the transition state. This bond is forming, so it's partially formed in the transition state. This bond is breaking, so it's partially broken in the transition state. What I really want to point out to you, though, it's going to be helpful to remember the fact that we're partially forming an alkene or a pi bond in the transition state. So that's going to help us once we know that we're forming an alkene or we're forming a pi bond in the transition state. That's going to help us understand the kinetics of elimination reactions. Okay, so one thing that you'll learn is that as you increase the substitution, remember, an SN2 reaction won't work at all on a tertiary substrate, and that's because this carbon is blocked. We have these three big groups. So hydroxide is not going to act like a nucleophile on a tertiary substrate. Let's say, for example, like we have tertiary butyl bromide. This carbon is very sterically hindered, so hydroxide is unlikely to attack this carbon and act as a nucleophile. So that pathway is shut down, so there's no SN2 reaction, right? Hydroxide is a good nucleophile, but it can't do an SN2 reaction on tert-butyl bromide. It's too sterically hindered. But elimination is actually quite favorable, and as you increase the substitution, that increases the likelihood of an elimination reaction, right? Because these hydrogens are on the outside of the molecule, so they're much more accessible. This hydrogen is not sterically hindered like this carbon is, so it's very easy for the base to come in and abstract this hydrogen. And what we're going to find actually is that as you increase the substitution, you increase the rate of reactivity, right? So in the E2 reaction, tertiary substrates will undergo elimination the fastest, and primary substrates will undergo elimination the slowest. Remember, this is the opposite of the trend for the SN2 reaction. So what we're going to find in a later video is that substitution is preferred as you decrease substitution, and elimination is preferred as you increase substitution. If you have a strong base, it can act like a base or a nucleophile. That's going to depend on the structure of your substrate. The more substitution will favor elimination, less substitution will favor substitution. So this makes sense intuitively, right? Because if you're a nucleophile, you're going to be attacking this carbon. As you increase the substitution, you're going to shut down that pathway. We can also understand it based on the structure of the transition state, right? So like I said a second ago, in the transition state, this pi bond is partially formed, right? And so the activation energy leading to an elimination reaction is going to be based on the energy of this transition state. So this is a potential energy diagram where we're starting off with hydroxide and tert-butyl bromide. We get to this transition state where this pi bond is partially formed, and then we come down to our elimination products. So what happens in the transition state as we decrease substitution? Let's look at how changing the substitution will change the energy of the transition state. So let's start with three different alkene or substrates. Let's say we have a primary substrate and a secondary substrate and tertiary one. Okay, so in the transition state here, right, this pi bond will be partially formed. Notice that that's a mono-substituted alkene. Similarly, this pi bond will be partially formed, and that's a mono-substituted alkene. But here, as we form this pi bond, we're going to get a partially formed di-substituted alkene. And remember in the previous video, when we talked about alkene stability, the more substituted that it is, the more stable that it is. So if we're partially forming a more substituted alkene, that's going to lower the energy of the transition state, which means that because in this transition state a more stable alkene is partially being formed, that this is going to be a faster reaction because it has a lower activation energy. This will be a slower reaction because it has a higher activation energy because a less stable alkene is partially being formed. Okay, the last thing that I wanted to talk about in terms of the E2 reaction is that you can have different hydrogens that are next to the leaving group. So when you're trying to decide what the product is of an elimination reaction, what you want to look at is one carbon next to the leaving group, right? We're forming an alkene, and this carbon is where the leaving group is, and we're going to form a pi bond between this carbon and one carbon next to it. So we have a hydrogen here that could get eliminated, or we have a hydrogen here that could get eliminated, or we have a hydrogen here that can get eliminated. These are called the beta carbons. You want to look at the beta carbons to decide where you're going to lose your hydrogen, right? Notice that if we lose this hydrogen or this hydrogen, we get the same alkene product, which would be a di-substituted alkene. But if we lose this hydrogen, we're going to form a tri-substituted alkene. And what we're going to find is that with a small base, like methoxide or hydroxide, the more stable alkene is going to be preferred because it's lower in energy. So we're going to pull off this hydrogen, lose the bromide. So the product is the more stable tri-substituted alkene. That's with a strong, small base. Okay? So this is called a regioisomer, meaning that you can either form alkene here or you can form the alkene here. This is one a possible isomer, otherwise known as constitutional isomers. But what if we had a really big base? What if we had tert butoxide? So now this base is really heavily substituted, is sterically hindered. This hydrogen is on a secondary carbon, and these hydrogens are on primary carbons, right? And so, actually, let me redraw this. So if we have tert butoxide, we have a sterically hindered base, and this sterically hindered base is so big that it wants to get an unhindered hydrogen, which is going to be this primary hydrogen is less hindered than the secondary hydrogen. So it's going to come in, pull off this hydrogen, form this double bond, and kick out the bromide, which gives this di-substituted alkene. So remember, this gave a tri-substituted alkene, right? So small bases like methoxide or hydroxide tend to give the more stable product. Large bases like potassium or sodium or tert butoxide will give the less substituted alkene because they're going to abstract a hydrogen that's less substituted. Let's talk about why in terms of kinetics, right? So if we have a small base like ethoxide, right, then we can abstract the more substituted hydrogen, and since we're forming a more substituted alkene in the transition state, that transition state is lower, so that product forms faster, right? But as we increase the size of the base, as a big base comes into contact with a more substituted hydrogen, that increases the energy of that transition state. So as we get to a really large base like potassium tert butoxide, we increase the energy of the transition state, right? So even though this product is still more stable, since the transition state is higher in energy, it's going to form more slowly. So this is called In this particular case, this product will be called the kinetic product because it forms faster, whereas this is the thermodynamic product because it's more stable. So with a strong, bulky base, you're going to form the less substituted product. With a non-hindered base, you're going to form the more substituted product. And the last thing to talk about is, let's say you had a scenario like this where you could form a trans or a cis alkene. Because you're partially forming a more stable trans alkene in the transition state, that is going to be formed faster always, so the trans is always going to outcompete the cis alkene product. Okay, to summarize, elimination reactions can happen by a concerted or by a stepwise reaction, but the E2 reaction is a concerted mechanism where the proton is abstracted, the pi bond is formed, and the leaving group leaves all in a single step. This exhibits second-order kinetics, so the rate depends on the concentration of the base and the substrate. The possibility that you'll see E2 elimination increases as you increase the substitution, which makes sense because substitution becomes more difficult as you increase the substitution on that particular carbon. The more substituted alkene is formed almost always. The only exception is when a hindered base is used, and we'll talk about there's only two hindered bases, one of which is tert butoxide that we just talked about. And when you have a choice, trans alkenes are always going to be favored over cis alkenes.